Hello everyone, my name is Syaraha Salwah, and today I will be presenting my research on CO2 removal, screening of phosphonium-based ionic liquids as an alternative for low-energy regeneration under the guidance of my advisor, Mr. Mohamed Faisal Taha. CO2 is a major greenhouse gas contributing to climate change. In industries, its presence lowers the quality of gases and causes pipeline corrosion. Traditionally, aqueous amine solutions are used to absorb CO2 due to their fast reaction rates. However, these solutions require significant energy for regeneration. An alternative is ionic liquids, ILs for short, which are salts that remain liquid at room temperature. ILs absorb more CO2 and are much less volatile than conventional solvents. Phosphonium-based ILs are particularly attractive because they are more affordable than other types of ILs. The challenge is that current methods like aqueous MDA solutions demand high energy to regenerate. This drives up costs and reduces efficiency, making long-term implementation difficult. To tackle this, we set two main goals: to synthesize and characterize 4 phosphonium-based ionic liquids and to screen the ILs for their CO2 absorption capacity, specific heat capacity, and cost of raw materials. So this research stands out for its innovative approach to CO2 removal by the following key aspects: low energy regeneration emphasis, using a comprehensive screening method, and focus on phosphonium-based ionic liquids as opposed to just amine-based. This research provides significant benefits by reducing energy consumption in CO2 capture, supporting climate change mitigation, and the use of affordable phosphonium-based ILs ensures scalability for relevant industries. It also offers strong commercialization potential due to its cost-effective synthesis of ionic liquids, wide applicability across multiple industries, and alignment with global market demand for emission reduction solutions. Now we will move on to the research evidence. The synthesis process was simple. We added acids to tetrabutyl-phosphonium hydroxide under reflux for 24 hours. This produced the ILs and water. The only difference among the 4 ILs is the type of acids used to introduce different anions. To confirm the structure of the ILs, we use two techniques: NMR or nuclear magnetic resonance, which checks the molecular structure, and FTIR or Fourier transform infrared spectroscopy, which identifies functional groups. These confirm the correct structure of all 4 ILs: TBP-PTSA, TBP-TFA, TBP-MESO3, and TBP-LEV. Next, we measured water content using Karl-Fischer titration, as water can affect both CO2 absorption and specific heat capacity. Results showed that TBP-PTSA and TBP-MESO3 had the lowest water content due to their stability of their anions. We also measured specific heat capacity using differential scanning calorimetry. Lower values mean less energy is needed for regeneration. Among the ILs, TBP-TFA had the lowest specific heat capacity at 1.69. We also tested the CO2 absorption capacity of all 4 ILs using a high-pressure CO2 absorption system and compared the results to the industry standard 30 weight % methyl diethanolamine. The results showed that TBP-LEV had the highest CO2 absorption, followed by TBP-MESO3, making them the most promising candidates. 3 criteria were evaluated: CO2 absorption capacity at 65%, specific heat capacity at 25%, and cost of raw materials at 10%. This weightage reflects their importance in practical applications. Using MCDM equations, we calculated normalized scores for each criterion. For CO2 removal, higher value is better. For specific heat capacity and cost, lower values are better. Now that we have determined the specific heat capacity, the CO2 removal capacity, and the cost of raw materials, we can determine the best ionic liquid. For CO2 removal capacity, TBP-LEV performed the best. For cost of raw materials, TBP-MESO3 was determined to be the most affordable with the lowest cost. And the final factor, TBP-TFA, excelled the most in specific heat capacity. After adding all the scores, TBP-MESO3 emerged as the best overall ionic liquid for CO2 removal, specific heat capacity, and cost of raw materials. In conclusion, from the screening, by considering all 3 factors, TBP-MESO3 is the best of phosphonium-based ionic liquid to be further studied for the optimization of CO2 removal. This can be done using 1 factor at a time or using RSM approach methodology. Thanks for watching!